Hey everyone, and welcome to This Explainer. Today we are taking on a really ambitious journey. We're going to deconstruct the entire planet. That's right, consider this your ultimate rapid-fire masterclass on Earth systems. We're going to look at exactly how our physical planet works, from the bedrock up, how the delicate webs of life are woven together, how human demands are kind of breaking those systems right now, and most importantly, the exact tools we have to fix them. So buckle up, grab a coffee, because we literally have a whole world of ground to cover.
Okay, let's dive into this. We've divided this massive topic into 6 core sections. We're starting with Earth's forces and hazards, then moving to ecosystems and fieldwork, followed by climate, water, and weather. After that, we hit resources and agriculture, then pollution and degradation, and we'll wrap up with sustainable management.
All right, Section 1, Earth's forces and hazards. Let's start with the literal foundation beneath our feet.
The ground you're standing on probably feels pretty solid, right? Well, it's actually part of a highly dynamic, constantly shifting puzzle. It's this endless battle of creation and destruction. Deep down, tectonic plates move apart at constructive boundaries. Magma rises up, birthing new crust and volcanoes. At destructive boundaries, they violently collide and subduct, causing massive earthquakes and, you guessed it, even more volcanoes. And at conservative boundaries, they just grind past each other, building up extreme friction until, snap, an earthquake hits. Meanwhile, up on the surface, weathering slowly tears rocks down. You've got physical weathering, like water freezing and expanding in cracks. Chemical weathering, which is basically acidic rain melting limestone away. And biological weathering, where plant roots literally wedge the earth apart over time. It's a wild system.
Now, all this tectonic movement brings some pretty brutal hazards. Earthquakes, they can cause catastrophic building collapse, trigger deadly tsunamis, wipe out water and electricity, and completely cripple local economies overnight. Volcanoes are just as ruthless. We're talking about lava destroying entire settlements, ash choking the air, halting transport, and totally ruining crops. So how do we actually survive this? Well, for earthquakes, human engineering is our best defense. By designing heavily reinforced, flexible, earthquake-proof buildings and staging rapid emergency aid, we actively manage the risk. We can't stop the ground from shaking, but we can definitely save lives when it does.
Moving right along to Section 2, ecosystems, biodiversity, and fieldwork. We're stepping up from the physical rock into the living layer of our planet.
Before we go any further, we got to nail down our baseline vocabulary. An ecosystem is the whole complex web of living organisms interacting with their environment. Think of a habitat simply as an organism's address. It's where it lives. Its niche, on the other hand, is its specific job or role within that neighborhood. Biodiversity is just the vast variety of all those species combined. And the ultimate goal tying this entire explainer together? Sustainable development. That means meeting our needs today without robbing future generations of what they're going to need tomorrow.
So why care about biodiversity? It isn't just some green buzzword, it's quite literally our lifeline. High biodiversity guarantees stable ecosystems, preserves absolutely crucial genetic diversity, provides our primary sources for medicine, and even drives significant tourism value. To protect it, scientists actually have to get out there and measure it in the field. They might toss down a quadrat, basically a square frame, to randomly sample plant populations. Or they'll run a transect line to see how life changes across a landscape. For bugs, they dig pitfall traps into the dirt to catch crawling ground insects. Or, my personal favorite, they use a tool called a pooter. Yes, a pooter. It's essentially a miniature human-powered vacuum used to literally suck up small insects for study. I know, funny name, but it's incredibly effective science.
Okay, let's look up. Section 3, Climate, Water, and Weather. We are transitioning into the massive atmospheric and hydrospheric systems.
Let's look at nature's most powerful engine, the tropical cyclone. It relies on a very specific and frankly dangerous sequential chain reaction. Step 1, it starts over warm oceans, which drastically increases evaporation. Step 2, this heavily moist air rises rapidly into the atmosphere. Step 3, that rising air creates an intense area of low pressure right below it. Step 4, as it gets higher, condensation occurs. And finally, Step 5, that condensation releases massive amounts of latent heat. This latent heat is the raw fuel that revs the storm engine, spinning the whole system into a devastating cyclone.
But you know, our overall climate is currently being artificially supercharged. The greenhouse effect is actually a completely natural process. Solar radiation enters, the Earth absorbs the heat, and then emits infrared radiation back out. Greenhouse gases in the atmosphere absorb and trap that heat, which keeps our temperature stable and livable. The real problem is the sheer volume of greenhouse gases we are suddenly adding. Every single time we burn fossil fuels, clear-cut forests, expand livestock farming, or fire up our cars, we are heavily increasing these emissions. It's like throwing a massive extra thick blanket over the planet, trapping way too much heat, and throwing the entire global thermostat out of whack.
And this atmospheric imbalance creates some truly devastating extremes. On one end of the spectrum, we have floods, driven by heavy rain, storm surges, and made so much worse by our paved, concrete cities. Floods destroy crops, damage infrastructure, and spread disease. We try to fight back with levees, drainage systems, and early warnings. On the total opposite extreme, we face droughts. These trigger horrific crop failures, famine, livestock deaths, and mass human migration. We desperately try to manage droughts with reservoirs and desalination. And then, throwing a massive wildcard into this whole mix is El Niño, a phenomenon that reduces ocean upwelling, totally decimates fish populations, and triggers erratic, extreme weather all over the globe.
So with all this chaos, how do we actually secure the water coming out of your tap? Well, aquifers are a huge part of it. Think of them as our hidden underground bank accounts. They store vital groundwater that remains reliable even during severe droughts. But we are dangerously overdrawing our accounts. Over-abstraction, low rainfall, and expanding cities are causing water tables to plummet. We also rely really heavily on dams. Now, dams are absolute miracles of engineering. They give us massive hydroelectric power, reliable irrigation, and flood control. But it's a trade-off. They come at an astronomical environmental cost, causing massive habitat flooding behind the dam, trapping vital sediment, disrupting fish migration routes, and often forcing entire communities to relocate. That brings us to Section 4, Resources, Energy, and Agriculture. We're shifting focus to human activity, how we extract what we need to survive.
Powering our modern world is honestly a complex catch-22. On one hand, renewable energy is sustainable, reduces greenhouse gases, and fights climate change with super low pollution. Sounds great, right? But the disadvantages are tough. Renewables are expensive to set up, heavily weather-dependent, require huge amounts of land, and can even cause visual or noise pollution. Fossil fuels, on the other hand, hold one major advantage. They are highly reliable right now, despite the massive pollution they cause. Then there's mining. The pros are obvious. It creates jobs, drives infrastructure development, and supplies the vital minerals we need for literally everything. But it comes at a steep and often totally irreversible environmental cost.
And feeding billions of people takes an equally massive toll on the Earth. Our endless demand drives aggressive deforestation. We clear forests for farming, logging, mining, and settlements, which leads directly to huge biodiversity loss, severe soil erosion, and spiking carbon dioxide levels. To boost our crop yields on the land we do have, we rely heavily on irrigation. Now, irrigation is a game changer for growing food in dry areas, but over time it can leave the soil poisoned with severe salinization. And then we have genetically modified, or GM crops, which, let's be real, are probably sitting in your pantry right now. They're incredible for yielding more food and resisting pests, but we have to weigh that against deeply concerning risks, complex ethical issues, expensive seeds that lock in farmers financially, biodiversity loss, and the very real risk of cross-pollinating with wild plants.
This leads us right into the darker side of things. Section 5, Pollution and Ecosystem Degradation.
Look at how aggressively we are stripping our planet bare. In the oceans, massive fleets equipped with advanced tech, rampant illegal fishing, and exploding global demand are driving severe overfishing. It's causing food webs to collapse and pushing species toward extinction. Meanwhile, on land, soil erosion driven by overgrazing, extreme weather, overcultivation, and deforestation is quite literally turning once fertile farmland into barren dust. It is desertification in action. It's a dual collapse driving massive crop failure, forced human migration, and terrifying biodiversity loss.
And it's crazy because even the ways we try to improve our land end up poisoning our water. Let's walk through the deadly chain reaction of eutrophication. It starts innocently enough. Nitrates and phosphates from agricultural fertilizers wash off the fields into lakes. Step 2, this massive nutrient spike causes rapid algae growth on the surface, which completely blocks out the sunlight. Without light, Step 3 happens. Submerged underwater plants die. Step 4, bacteria massively multiply to decompose all those dead plants. As these bacteria respire, Step 5, they consume almost all the available oxygen in the water. The oxygen decreases so drastically that, Step 6, the fish quite simply suffocate and die, just from a little fertilizer runoff.
Up in the atmosphere, our industrial waste creates another insidious chemical hazard. When we burn fossil fuels, sulfur dioxide and nitrogen oxides are released straight into the sky. These toxic gases dissolve directly into the moisture up in the clouds. That mixture forms potent sulfuric and nitric acids, and when the weather finally breaks, this toxic cocktail rains straight back down onto us as acidic rain.
The collective collateral damage of our industrial footprint is just staggering. Acid rain directly damages forests, acidifies the soil, and kills aquatic life. General air and water pollution accelerates global warming, damages plant life, causes severe biodiversity loss, and triggers human respiratory diseases. In our oceans, massive oil spills poison marine life, reduce oxygen exchange, and absolutely wreck coastal economies. We try to fight back using floating booms and skimmers to contain the oil, but it's an uphill battle. Finally, on land, heavy rainfall causes leaching, which washes vital nutrients deep underground where plant roots can never reach them, permanently reducing the fertility of the soil.
All right, take a breath. It is a grim picture, I know, but it is absolutely not hopeless. Let's move to our final segment, Section 6, Sustainable Management and Conservation. Let's talk solutions. First, let's look at how we reclaim our most precious resource, water. To secure clean drinking water and safely handle what goes down our drains, we've engineered rigorous treatment processes to prevent disease. Step 1 is screening, literally catching the large debris. Step 2 is sedimentation, letting the heavy sludge settle out at the bottom. Step 3 involves biological treatment where bacteria eat the organic waste in sewage, or for drinking water, running it through incredibly fine filtration. Finally, Step 4 is a targeted blast of chlorination to kill any remaining biological threats. Once it's completely safe, Step 5 is storage and distribution, sending it right back to your tap.
And here is our ultimate master toolkit for global survival. To save the oceans, we enforce strict quotas, implement closed breeding seasons, and ban destructive gear to make fishing sustainable. To save the land, we deploy contour plowing, terracing, and crop rotation for serious soil management. We absolutely must build sustainable cities, powered by green energy, widespread public transport, and integrated green spaces. We can fund these protections through ecotourism, which is great for generating local jobs, but we have to be super careful to manage the litter and habitat disturbance that tourists bring. In parched, drought-stricken areas, desalination offers virtually unlimited drinking water from the sea, though we have to solve its high energy demands and toxic brine output. And ultimately, heavily protected national parks and targeted captive breeding programs remain our absolute best direct conservation methods.
So, there you have it. We have the knowledge. We understand the Earth's forces, the biology, the immense damage we've caused, and we clearly have the toolkit to fix it. But I'm going to leave you with this provocative thought to ponder. When you look at the sheer, mind-boggling scale of the global demand and pollution we just went through, are our sustainable management solutions truly scaling fast enough to outpace our deeply ingrained, destructive human habits? It is without a doubt the most critical question of our time, and how we answer it will determine the future of this planet. Thank you so much for joining me on this explainer, and keep questioning the world around you.